Hello, welcome back to the Integrate Intelligently podcast. I'm your host, Jeff Brickler. And after a short, brief pause, Scott and I are back for the Integrate Intelligently podcast. Scott is the founder and CEO of CAD Talk Software. He and I are brothers, been working together here for 10 years. So Scott, welcome back, middle of the summer here as we're recording. And how's things been so far?
Oh, it's been great. It's been great. It's been a good summer. It's the weather's kind of starting to cooperate finally. And it's been some nice sunny days around here. Hot, but sunny and nice.
Yeah, my summer's been a bit chaotic, actually, quite a bit of travel. I think I was gone a couple of weeks in June, and then looks like I'm going to be gone a couple of weeks in July. And so it's been a bit chaotic for me, but glad to be back here recording with you. And so today we have an interesting topic, Scott. We're going to talk about DFM and what DFM is and kind of what we know about it. So think of this as like a DFM 101. Like, what is it? Another acronym, of course, right? Yet another acronym in this industry. So let's talk a little bit about DFM. Maybe Scott, define it for us. Tell us what it is.
Sure. So like DFM is an acronym for design for manufacturing. Typically, it's the act of, a lot of times, it's kind of the act of making sure that your design is more conducive to how you're going to make it. So you take into account more of the manufacturing process in your design. And not that I think a lot of engineers would typically do that, but it's, sometimes some companies are better than others. And you typically see it in situations where you have more high production, like there's more volume, because they're trying, if you're making, hundreds or tens of thousands of parts or whatever it is, or those things, then every little improvement in that manufacturing process scales pretty well, right? But you also see it in kind of more, and as you scale down the sizes too, because you're trying to reduce costs, you have material availability, you're trying to reduce lead time and things like that. So there's benefits to even doing it on low production, but you see it a lot with high production works. A lot of it's the act of figuring out how do I optimize for manufacturing during the design stage. During design, your first thing you think about is how do I make this thing work? And then you think about how do I make it easy to make? That's usually how and then how do you make it easy to make is the DFM.
Right. I remember when we were kids and we were out there in the garage working with our dad and on the car, and Dad always used to say, I'm sure we did too, kind of cursing the engineers who designed the vehicle. You're like, why'd they put this bolt here or whatever? Yeah. And probably to your point, in those high production environments, they probably were designing and optimizing for manufacturing. Right? They weren't optimizing for you and me, no. Who they're lying on the ground in a puddle of some kind of grease or nastiness, trying to get to a bolt, on transmission somewhere. They weren't designing for that, right? They were designing for, right. I think the design principles: form, fit, and function. Right? Does it form and does it fit in the function? And then, of course, another avenue might be manufacturability, or and the design may make sense for those things. It may not make sense for the aftermarket guys working on it.
Yeah, they're not designing for maintenance; they're designing for manufacturability. A good example of that might be when you're putting the engine in, if you're working on the engine or you're working you're doing it in an assembly line, it's probably suspended by a jack that's really easy to step under or get around. So the conditions in the factory during manufacturing aren't the same conditions during maintenance. And that brings up a good point about engineering in general. Everything from an engineering perspective is a game of optimizations. So you're constantly trying to figure out what you're optimizing for. I even tell our engineers that. It's they always go, what should I do here? I'm like, well, it depends on what you're optimizing for. And because it'll change your decision tree on everything that you do. You're are you trying to make it cheaper? Are you trying to make it faster? Are you trying to make it easier to change the code or change the design? What is it you're trying to optimize for? And typically you can only optimize effectively for a few things. And then there's always these trade-offs. I know in code, you could typically code that runs faster tends to be harder to read. So so that you kind of have a conflicting optimization there. And then the same thing, sometimes you can make things cheaper to make, but then they're not as easy to work on, so you're kind of trying to balance all of these things together when you're optimizing. So designing for manufacturing would be DFM would be optimizing on what the constraint of how we're making it, which also could make it more expensive, least from a material standpoint, or make it harder to work on, like your example earlier of like the maintenance side of it. So those are all things like that, because when you optimize for one thing, something else gets harder or usually worse.
Yeah, I mean, firsthand, right? Firsthand in life. Definitely when I was working on cars, we were working on cars. I remember that time we were working on your transmission for that F-250, and it was not optimized to work on in a garage in the winter on the ground. I was definitely not optimized for that. So it's a good point that engineering is about optimization, and manufacturability or designing for manufacturability is one optimization that an engineer has to keep in mind.
Yeah, and you're balancing that. Like if you think about it from a manufacturing company perspective, designing it obviously to work, which would be the table stakes, right? It has to do the job. And then you think about like from a company perspective, what do you care about the most, right? If you're trying to provide equity or whatever value to shareholders, a large organization like a big automotive company or manufacturing company, you're going to optimize on what gives you competitive advantage and what decreases cost. So so decreasing costs would come in the factor of like material costs that you're looking at, or the manufacturability. The easier it is to manufacture, the less labor and other things you're putting into that process. So they tend to optimize for that at the detriment of the other side. Whereas and then there's different philosophies in different companies on what they should optimize for. Right. I mean, it was like, I know with like Mercedes-Benz, they very much optimize on maintenance. Like, I remember Dad telling us that like there was like a little toolkit that used to come with Mercedes or BMW, I can't remember which one. And you could take the entire car apart with that little toolkit that came with the car. Like it was completely designed for maintenance and things like that. It was like, so that's just another engineering principle, a different level of optimization they're looking at. But but generally you see people trying to optimize on what they're trying to do. They're trying to make a product at a good price point that the market will buy, and in a fast, decent lead time. And optimizing for manufacturability tends to help with that with that type of with that optimization, with that thing you're trying to. Those things are served well by design for manufacturing.
So I understand that. I understand design for manmanufacturing, like you said, for products that you make all the time, right? That you're going to optimize for. Cars and that sort of thing, or other products that you might design on, which means you might design with a certain material type, right? Instead of think about wood, instead of making it out of plywood, you might make it out of like Oriental strand board or fiber board or like cabinets, right? You might make optimizations to make it cheaper. Is it as durable? No, it's not as durable, but it's cheaper, right? And I can make more of them and keep material costs down, and more people can have these things or that sort of thing. So that makes sense if you're making them in mass. But what about like project-based manufacturing or where you've got a lot of what we call low volume, high mix, right? Where you have lots of different choices to make, not just choices, but you have different products, right? The product's slightly different, or how does DFM, how would that work in that realm? And how could engineers design for that?
Sure. And I think about an example I did when I was working in, an engineer to order packaging machine company that we talked about before. A lot of times it's around standardization. So you're optimizing around standardization to decrease lead time. So you have variability in the end product, but consistency in the raw materials. So you might say we're gonna standardize on, like, one of the things that we did was we standardized on certain thickness of material for fabrication. So we did this machine. We were building a machine, and we said we're gonna only make the machine out of 7-gauge stainless and 3/8 stainless. So on a part by part level, there probably was some over engineering on some of those pieces, but it allowed us to have consistency because we knew that the less material switches that we had on the laser, the easier it was to get higher utilization of the laser, and then to get parts through the laser operations faster, which then decreased the throughput, increased the likelihood of all the parts being delivered together for assembly. So the lead time was down. So we optimized on lead time reduction. And lead time reduction, there's books about this there's one book called Quick Response Manufacturing that says in high mix, low volume, you tend to do really well optimizing on lead time reduction. And you can design for that by driving more consistency in the process, like using the same hardware, like 2 or 3 sizes of nuts and bolts, or maybe 1 or 2 sizes of nuts and bolts, using the same raw materials so you can fabricate them together. Having a lot of consistency around that process, even though the parts may change, how you're making the parts are very consistent. So you're just driving more consistency to earlier in the process because you don't have the consistency in the product itself.
Yeah, it reminds me, you don't say it as much anymore, but I remember, I don't know how many years ago, even before I joined CAD Talk, and I think you used to say this phrase, this rhyming phrase of consistency drives efficiency.
Oh, it's true. Yeah.
I think that DFM, this idea, design for manufacturing, is driving consistencies where you can and getting that information to the engineers during design time to just drive that efficiency, right? To make better choices of materials, make better choices of, because the type of materials also affects how you route the parts to the shop, or if you have certain lasers that run better than others, right? Those run times, how long those things take. Those types of optimizations, even if you have inconsistent or high mix, you can, like you said, drive efficiency through the materials and the machines that you have.
Yeah, I think that the idea of that, you think about it with, if you had mass production, let's use that example, like mass production, you're making a lot of something. You can drive more cost basis on your design for manufacturing because you're making so many that any one part can be optimized for batching, right? Because you're making like 1,000 crankszafts, you're making like those types of things, and you can do that. So you can try to drive the cost of the crankshaft or whatever that thing is down as much as possible. But if you don't have as much volume and you have a lot more mix, then you want to drive the consistency part of it. You're not going to have enough volume to get the consistency that you want. So you want to have consistency more of the raw material stage. Like if I'm making like 5 different parts, but I'm going to make them out of the same bar stock, then I could put the bar stock on the saw and cut all the different parts out of the one bar stock, and I can reduce the setup. You see how that? So now you're still optimizing, but you're optimizing earlier in the build cycle, as opposed to later and things like that. So it's just like you have to know your mix and kind of what you're making and things like that. The DFM principles would change based on those variables. Yeah.
Well, Scott, this is a good introduction here to design for manufacturing. I know this was really supposed to be like a primer, just an introduction to design for manufacturing. So a little preview into our next episode, we're going to dive a bit deeper into design for manufacturing, more than just like what it is, but how to use it. What if you don't have a manufacturing engineer? What if you have other challenges beyond that, right? What does ideal look like, and how you might implement this in your own company? So Scott, thanks a lot for joining today. If you want to download our free white paper or our white paper, look in the show notes, subscribe to the CAD Talk Integrate Intelligently podcast, wherever you get podcasts, whether that's on here on YouTube or Spotify or Apple Podcasts. Feel free to follow me or Scott or link with us in our LinkedIn profiles. You should look for, of course, Scott Brickler at CAD Talk and Jeff Brickler at CAD Talk. Be warned, if you look for Jeff Brickler, you might find more than one. We have a couple of those guys in the family, so just be warned. You want the one at CAD Talk. So Scott, anything else you want to add before we close up and plan for the next episode?
No, I think this is a great topic. Looking forward to talking about it some more on next episodes.
Great. Thanks, everyone.